Every second, our star, the sun, burns with unimaginable power. But sometimes it loses control. Huge explosion erupts from its surface, flares so bright they could outshine billions of hydrogen bombs, and waves of plasma big enough to swallow planets. These are solar storms, violent tempests that can reach Earth, knocking out satellites, power grid, and painting our sky with glowing auras. But what exactly are they? How do they form? And what happens when one headed our way? The sun isn't a calm ball of fire. It's a giant magnetic tangle. Its equator spins faster than its pole, stretching and twisting magnetic field line like a rubber bands. Eventually, these tangled line snaps, releasing an enormous burst of energy. This process, called magnetic reconnection, launches intense radiation and jet of charged particles into space. These explosions often happen near the sunspot, dark patches where the magnetic field is strongest. And when the field finally breaks free, two powerful phenomena are unleashed: solar flares and coronal mass ejection. Solar flare. Think of a flare as a sudden flash, a burst of electromagnetic radiation. When the sun magnetic knots untangle, energy explodes across the spectrum, from X-ray to the visible light. Some of these flares are so strong they can outshine the sun's normal brightness for minutes. NASA called them explosion in the sun atmosphere. The most powerful X-class flares send radiation racing towards Earth, arriving in just 8 minutes. They can disturb our planet's upper atmosphere instantly, disrupting radio signals and GPS. While flares are flashes of light, CMEs are explosions of matter. Imagine billions of tons of charged gas plasma hurled into space, traveling at millions of kilometers per hour. When a CME is aimed at Earth, it can slam into our magnetic field, triggering a geomagnetic storm. That's when things get serious. Satellites, power grids, and even our atmosphere feel the impact. Solar energetic particles event. And then there are solar energetic particles, supercharged bullet of radiation. These particles are flung out of flare or fast-moving CMEs. They zip through space, reaching Earth in the little as 30 minutes, bombarding satellites and astronauts with a dangerous radiation. Solar flares travel basically at the speed of light, just 8 minutes to reach Earth. Energetic particles took like half an hour, but most of the CMEs take 1 to 5 days to reach Earth. But the fastest one, like one on July 23, 2012, crossed the 150 million kilometers in just 20 hours. If that one had hit us, we would be telling a very different story. When a solar storm slams into the Earth's magnetic shield, the result can be electrifying. Power grids, electric current induced in ground can overload the transformer. In 1989, Quebec's power grid collapsed in just 90 seconds, leaving millions in darkness. And in satellites, charged particles can damage electronics, distort signal, and even drag low-orbit satellites closer to Earth. In GPS and radio, intense X-ray from the flare disturb the ionosphere, blocking radio and GPS signals, especially on the day side of the Earth. In aviation industry, during major radiation storm, airlines reroute flights away from the poles to protect the passengers and the crew. In this messy situation, one of the most beautiful effects are the auroras from these particles. Storm-driven particles ignite the glowing curtains of the light in the sky, sometimes reaching latitude as far as the south as India or Caribbean. One of the most interesting historical facts is that we have been hit before by these storms. The Cartesian event of 1859 was the biggest solar storm ever recorded. It wasn't just a light show in the sky. Telegraph lines caught fire all around the world, sparked the shocked operators, and the auroras lit up the tropical region, and people wake up thinking the sun was out. Then came the 1989 storm that darkened the Quebec and the near miss of 2012. That superstorm missed us by just a week the sun's rotation. Experts agree that had the 2012 storm hit, the resulting geomagnetic chaos could have crippled the modern technology, resulting in the global blackout lasting weeks or even months. It was a stark reminder of our vulnerability. The good news is that we are no longer blind. NASA and the National Oceanic and Atmospheric Administration maintain a fleet of dedicated Sentinel satellites watching the sun every second, tracking flares and CMEs. Crucially, real-time sensors at the L1 Lagrange point, such as Deep Space Climate Observatory, give us the final warning. This system provides a window of 30 to 60 minutes before a storm main magnetic wave hits us. That may not sound like much, but in the world of space weather, that's the difference between safety and chaos. With a cutting-edge space mission like Parker's Solar Probe and the Solar Orbiter, we are learning more every year, getting closer to predicting the sun fairies' mood before they explode. The sun gives us life, but every flare, every eruption is also a powerful message from 150 million kilometers away. It's a stunning reminder that even in our high-tech connected world, we still live beneath the spectacular volatile weather of a star.